All right then, econ friends, welcome back to our next video. In our previous video, we dissected and introduced the cartel model, aka a model of collusion in oligopoly. And we determined that cartels are inherently unstable because the firms that join a cartel, that come together, they face two conflicting incentives: the incentive to cooperate and the counter incentive to violate. This is a really, really important idea, not just in economics, but in any aspect of social life, business, politics, the legal system, all these different venues where we think through the need for cooperative arrangements, okay? Because of the power of this, a great, somewhat complicated, but really rewarding field has emerged, initially in political science and now adopted in many, many fields, ranging from economics, finance, law, military. And we call this idea, we call this way of thinking game theory. We're going to focus in this video on game theory. Now, there's a lot to cover. My advice to you would be, when it comes to game theory, focus on three different things. Number one, the jargon. There's going to be a lot of brand new jargon, so make sure you take the time to learn what the different terms mean. Number two, the second focus is on kind of the top level view of interaction and cooperation. You want to keep that in mind as you go through this. And then level three is the on the ground, in the weeds tactical level, where I'm going to share with you a couple of different models, okay? Practice this stuff, be really fluid in your thinking, because if you can get your head around game theory, never mind oligopoly, you'll really have an advantage in understanding lots of other interactions in everyday life, because we increasingly see game theory everywhere, okay? With that said, let's jump in. And let's start, as always, with definitions and terms. Game theory, my friends, is defined as the study of strategic behaviors. Strategy implies making decisions not just around your own ideas, but around your ideas as well as the anticipated reactions of others, okay? Strategy involves your own decisions, but making your own decisions with an awareness of the potential reactions of rival players, all right? Game theory is the study of these strategic behaviors, and it's the study of the ways in which individuals or other entities, right? Individuals, firms, businesses, governments, armies, how all these different entities make optimal decisions by anticipating. Key thing here, by anticipating how rivals will respond to their actions. Notice again that this is new. When we talked about monopoly and PC and MC, we made the decision and that was it. In none of those three models did we make the decision and then ask ourselves how it would be seen by rivals. This is the first time we're going to do it. So let's take our time and jump in, okay? Again, game theory, the study of strategic behaviors, which really is all about anticipation and response. Now, in the language, in the jargon of game theory, a game is basically any interaction between people, okay? So don't be fooled by the term game. A game in economic game theory is simply a shorthand term for any interaction. Broadly speaking, in economics, we believe that games can either be, number one, simultaneous move games, or number two, sequential move games. In a simultaneous move game, the firms are making their strategic decisions at the same time, simultaneously. But notice that what's really critical here, it's not just that the firms are making their decision at the same time, it's that because two different firms are deciding at the same time, each firm is making a decision, here it is, without the full knowledge of the actions of their rivals. So a simultaneous move game, it's not just about the fact that you and your rival make the decision at the same time, kind of like a kid playing rock, paper, scissors. It's not just that, it's that in a simultaneous move game, you're forced to make decisions without full knowledge of what your opponent is doing. In contrast to that, we have what are called sequential move games. In a sequential move game, the firms make their strategic decisions in sequence. I make a decision, then you make a counter, then I make a counter, and it goes back and forth. Because of this, critically, in a sequential move game, the firms will make their strategic decisions with full knowledge of the prior actions of their rivals. There's not one better or one worse here. It's just important to understand that because of the way that games can be modeled, firms have to think of different ways to act. Sometimes you act with information. Sometimes you act without information. All those things add to the complexity and the nuance, but also the rewards of studying game theory, okay? Let's talk first about simultaneous move games. When we talk about simultaneous move games, we need to have a model. This is about the models. We can model a simultaneous move game by using what we're going to call a payoff matrix. A payoff matrix refers to a graphical representation of a simultaneous move game. And critically, a payoff matrix demonstrates the different actions that firms can take and their different potential payoffs. Or instead of payoffs, we can maybe say benefits. Let's take a look here at an example of a really simple payoff matrix. This, to keep it easy, is a quantity decision. So we imagine here that we have two different players. We have Romeo, we have Juliet. They're rivals, okay? They compete against each other, and we're going to assume, just to assume it for shits and gigs and to make the model easier, that this is a duopoly. A duopoly, duo, is an oligopoly with only two players, okay? So we're assuming here that Romeo and Juliet are rival players in a duopoly, and they each have to make a production decision. How much to produce? Notice that we put Juliet up here and Romeo here. Notice also that both Romeo, player one, and Juliet, player two, face one of two output decisions. They can either decide to produce 3 units, or they can decide to produce 4 units. So you see up here with Juliet, decision 1, making 3, decision 2, making 4. And you see right here on Romeo's side, decision 1, produce 3, decision 2, produce 4. So we start off a payoff matrix by identifying the different players. Got that? By identifying their different options. Got that? What's left over, my friends, are these 4 squares right here. And these 4 squares represent the different payoffs, the different benefits that each player will get based on decisions. I like to make this easy by numbering my squares. So let's call this one here box 1, box 2, box 3, and box 4. As an example, as you look at this, let's say that we're talking about box 1. Box 1 is the payoff matrix. It's the benefits, it's the results, it's the outcomes if, because we're here in box 1, if Juliet decided to make 3, and so did Romeo. So if Romeo says, I'm going to make 3, and Juliet says, I'm going to make 3, we go across at 3, we go down at 3, and this right here becomes the box that we are analyzing. And we would see in this case that, for example, if Romeo makes 3 and Juliet makes 3, then Romeo, who is blue, would earn profits of $18. And Juliet, who is red, would also earn profits of 18. We also see other payoffs. Let's say that hypothetically, let's change our colors for some contrast. Let's say that Romeo decides to make 4 and Juliet decides to make 3. Well, 4 is here and 3 is here, so we'd be in this box. So if, hypothetically, Romeo decided to make 4 and Juliet made 3, Romeo would earn profits of 20 and Juliet would earn profits of 15. We can look at the 4 different outcomes, right? 2 players, each with 2 options. 2 times 2 is 4. We have 4 potential outcomes. Those, my friends, are modeled on a payoff matrix. You can see that right there. There's some outcomes that are more beneficial than others. Keep that on your back burner. We're going to come back to it, okay? Now, going back to the jargon, in the language of game theory, we learn that games can be simultaneous and sequential. We also believe in game theory jargon that outcomes, which are also called solutions in the sense of which square we land on, that those can either be what we're going to call A, cooperative solutions, or B, non-cooperative solutions, okay? Let's dissect this a little bit. Again, more jargon, but get through it. A cooperative solution is the outcome that occurs when players collaborate. This is the key. Cooperative solutions occur when the different rivals collaborate. In other words, when the cartel makes an arrangement and keeps it. You can see the cooperative solution as the best possible outcome for the players when you view the outcome collectively. So a cooperative solution will lead to the best possible solution for the cartel as a whole, for the game as a whole. A non-cooperative solution, on the other hand, this is the outcome that occurs when players do not collaborate. When players do not collaborate. And instead of collaborating, when each player says, the hell with him, I'm going to pursue my own self-interest. You can see the non-cooperative solution as what happens when the cartel that we discussed earlier breaks down. When each player says, screw the arrangement, I'm going to violate, I'm going to produce more to maximize my profits, and the hell with them. So again, we have the language, the jargon. We're going to have cooperative solutions and non-cooperative solutions. All these terms come together in a critical concept, the concept that we call dominant strategy. A dominant strategy has a specific definition, my friends. A dominant strategy refers to a strategic decision that is the best decision, and this is the key, regardless of what your rival does. Okay? A lot to take in. We'll say it again, and then we'll do a little model of it. A dominant strategy refers to a decision that you would make regardless of what your rival does. In other words, if your rival has several different options, and regardless of what option your rival does, your decision is still the same, you, amigo mio, have a dominant strategy. Now, let's first dissect it, and then let's understand the power of it, because the dominant strategy thing is really what makes or breaks the cartels that we talked about in the last video. In order to determine dominant strategy, the easiest way is to take the matrix and pull it apart. Okay, so let's start right here in panel A. Let's dissect this, panel A. In panel A, here's what we're looking at. Suppose that we start off, and in panel A, we're analyzing Romeo's decision. So panel A, right here, we're asking ourselves, what should Romeo do? Check it out. Juliet, we decided earlier, can either decide to make 3 units or 4 units. Let's dissect this. Let's say that Juliet makes 3 units. If Juliet makes 3 and Romeo makes 3, Romeo makes $18. If Juliet makes 3 and Romeo makes 4, Romeo makes $20. So clearly, if Juliet makes 3, Romeo's best bet, make 4. Now let's see what happens if Juliet decided to make 4. If Juliet makes 4 and Romeo makes 3, sorry, do it here. If Juliet makes 4 and Romeo makes 3, he makes $15. But if Juliet makes 4 and Romeo makes 4, Romeo pulls in $16. So if Juliet makes 4, Romeo's best bet, make 4. Notice what this means. No matter what Juliet does, whether she makes 3 or makes 4, Romeo has the same best solution. Make 4. Therefore, for Romeo, producing 4 is a dominant strategy. It's a dominant strategy because it's the best decision for him, regardless of what Juliet does. Okay? Now let's go to the other side of this equation. Let's look at our friend Juliet up here in panel B. So in panel B now, we're analyzing Juliet's decision. Same analysis, just backwards, okay? If Romeo decides to make 3, Juliet can make 3 and she'll earn $18, or Juliet can make 4 and she'll earn $20. So clearly, since 20 is better than 18, if Romeo makes 3, Juliet's making 4. Let's say, on the other hand, that Romeo decided to make 4. If Romeo made 4 and Juliet made 3, she would pull 15. If Romeo made 4 and Juliet made 4, she would earn 16. Since 16 is better than 15, then if Romeo makes 4 units, Juliet will also make 4 units. And notice now that for Juliet, we also have a dominant strategy. Make 4, produce 4, set Q equal to 4. Because no matter what Romeo does, whether he makes 3 or makes 4, Juliet is best off making 4. This, therefore, is her dominant strategy. Okay? Now, you're asking the question, okay, well, so what? Let's put all this knowledge together. Let's make this box 1, box 2, box 3, and box 4. If you take a look at this, if Romeo and Juliet formed a cartel, right, formed a collusive arrangement, decided to act as if, the cooperative solution, in other words, the best possible outcome for them would be here in box 1, because in box 1, their combined profits, their combined money is the best. In box 1, the combined money is 36. In box 2, it would be 35. In box 3, 35. Box 4 sucks. In box 4, the combined profits are 32. What we would say is then that the cooperative outcome, the cooperative solution would be box 1, with profits maximized, $36 for the whole, $18 per person. Beautiful. But it's not going to happen, because we just showed up here that both Romeo and Juliet have a dominant strategy of Q equals 4. And therefore, even though the even though the cooperative solution, the best solution is right here in box 1, where Q equals 3 and Q equals 3, nope. We predict that because of their dominant strategy of making 4 each, Juliet will make 4, Romeo will make 4, and we're going to end up here in box 4. And ain't that a bitch? They could have walked away with a combined 36 in the cooperative solution, but instead, because of the nature of the incentives, because of the complexity of the payoff matrix, instead, they're going to wind up actually at box 4. They're going to end at a non-cooperative solution, at a non-cooperative outcome. This, my friends, is the paradox of game theory. This is the reason why cartels are unstable. This is the reason why there is incentive to violate. This is why cartels fall apart. The payoff matrix that we just learned, the implication is that what's good for the one can be bad for the many. And what's good for the many can be bad for the one. The incentives fight each other. And as a result, even though Romeo and Juliet, had they been able to form and sustain arrangement, even though they would have been here at box 1, we predict ultimately that it's going to fall apart, that the incentives to violate will get in the way, that dominant strategies will dominate, and that instead we're going to end up here at box 4, a completely suboptimal outcome. Okay. Another quick term for you that you may have heard that is related is the idea of a Nash equilibrium. A Nash equilibrium is an outcome in which no player can improve through a unilateral action. Oftentimes, not always, but often, the Nash equilibrium occurs at the non-cooperative outcome. So in this case, even though Romeo and Juliet would both be better off making 3 and maximizing profits there at box 1, they're likely going to find themselves in a Nash equilibrium in box 4. Okay. In other words, a Nash equilibrium can be seen when each player is doing the best that he or she can do given the actions and the perceived reactions of a rival. Okay. Now, this idea that I just outlined to you is super powerful. In fact, it's so powerful that it has become a classic in game theory. And it goes by the name the prisoner's dilemma. You may have heard this before, okay? We just did it, but I'll define it for you. A prisoner's dilemma is a classic game theory condition. In a prisoner's dilemma, as we just learned, the two players would both be better off under a cooperative solution. But instead, they fail to reach the cooperative solution because they face individual incentives that push them out of it, okay? So a prisoner's dilemma refers to a classic game theory, a classic outcome in which the counter incentives take them from a cooperative solution, which would be optimal, to a non-cooperative solution, which is suboptimal. In other words, they fail to reach the the cooperative outcome. It's called a prisoner's dilemma because, as we just did with Romeo and Juliet, you can do it, imagine that there's two prisoners. The classic is Bonnie and Clyde. We take these as two rivals in a cooperative game, bank robbery. Let's say that they're arrested. The police are leaning on them to testify against the other. Both Bonnie and Clyde have two potential actions: provide evidence to the coppers or provide no evidence by zipping it. If we put our numbers down, box 1, box 2, box 3, box 4, we see a payoff matrix. We see that based on what Bonnie does and Clyde does, there's potential jail terms. Obviously, in this case, the cooperative outcome would be here in box 1. This would imply that both Bonnie and Clyde, that they zip it, that they don't testify against the other, that they're quiet, and they would only get maybe 1 year. Notice that box 1 is the optimal outcome for the group, because in box 1, the total jail time is less, 2 years, compared to 12, 12, and 12 in the other boxes. But if you were to suss out the dominant strategies, what you would find is that even though both Bonnie and Clyde together should zip it and land here in box 1, the dominant strategies are going to lead them down here to box 4. And instead of getting 1 year each, they're probably both going to testify against the other because of the dominant strategy, and they're going to land at a suboptimal solution, each of them doing far more jail time than if they had zipped it, okay? If you want, pause the video for a minute, take a look at this payoff matrix, separate out the decisions, and see if you can identify the dominant strategies, okay? If you can do that, you're well on your way to understanding this, okay? So that, my friends, is the prisoner's dilemma. The big takeaway here is to understand that the prisoner's dilemma, it can help us to really see and understand the incentives and therefore the predicted behaviors of the different players in the collusion cartel model that we studied earlier. Okay, while price and output fixing would be great for the cartel, they would be the cooperative solution best for the cartel as a whole. We can now predict that the incentives that each individual firm faces will ultimately cause the cartels to fall apart and end up at a suboptimal, non-cooperative solution, box 4 and not box 1. Of course, the firms themselves recognize this. So at the same time that each individual firm faces incentives to violate the arrangement, the cartel as a whole is also incentivized to find new, innovative ways to cooperate in the future. This is why we see in game theory and in oligopoly these rises and falls at times of oligopoly cartel power. They form the arrangement, it's going well, and then it fails. And we know why from game theory. But the cartels also know game theory. They also know about the incentives to violate, and therefore they're always looking for new incentives, new structures to prevent the violation. This is the strategy that's involved in these models, okay? So that, my friends, is enough for this video. We've covered the idea of simultaneous move, which is modeled by game theory and the payoff matrix. You now have a way to understand the incentives that were guiding the cartels. And hopefully now with this model in mind, you understand a little bit about how cartels come together, but also why they fall apart. In our next video, I'm going to take an extension of this and do a little bit of analysis of sequential game moves. But that's for the next one. Thanks for tuning in, my friends. See you next time.